Hello everybody, welcome back to another session with calculus. Today we will be talking about continuity. So this is going to be a portion of calculus where you're not going to be doing a lot of like algebra per se, but instead you're going to be doing a little bit of, well, a lot of proving if anything. So, you know, if you had a really good time back in geometry, then this might be for you. But if you didn't, then, just kind of brace yourself a little bit and strap on, and we'll try to get through this as much as as early and as swift as possible. So first we're going to start off with some definitions for continuity. So here the first three that we have is will be the ones that are in blue. The first one being here, we have f is continuous. The word continuous is what we're trying to define at a certain point x is equal to a. And in order for us to show that, or the formal definition for it is the following right underneath. In order to show that f is continuous at a certain point, we have to show that the limit at x equals to a for f of x has to be equal to a then. Is equal to f of a. Then the two underneath of it, if f is continuous from the left-hand side at a point x is equal to a, the limit you have to show that as x is approaching towards a from the right-hand side is the same thing as just plugging it into f of a. And the last one over here is f is continuous from the left-hand side of the point x is equal to a. We have to show that the left-hand limit is then equal to the same thing as just plugging into the f of a. So these right here, for the most part, I think for our viewers, at this point, it's going to be pretty trivial. So when we get to a proof, I think it'll become more relevant. So we'll come back to this and we'll put more emphasis on it then. From that, we're going to extend to the next part to say how is f is continuous on an open interval or on a closed interval of a to b. So that's where this next part comes in then. F is continuous. The way we define continuous on an interval of a to b is if f is continuous for all values of c inside that interval. Okay, so that means that we have to show that every single value of c that is between a and b will be continuous. Now, does that necessarily mean we have to literally do that for every single one of them? The answer is no. When we do a proof, we usually show that for some variable c inside the interval that this is going to work out. So again, when we do a proof, you'll see how this is actually going to work in a little bit. Now, to show you something a little bit more concrete, let's go ahead and show the different types of discontinuity that you're going to be running into then in calculus. The first one you've seen already, which is called a removable discontinuity. So what that means is on a graph right here, removable discontinuity is where you're going to have a graph and then you have an open circle and then afterward you have a continuation of the graph. So you can see for this function that I created, this is not a continuous function because you have to lift your finger or you have to lift your pen in order to draw the rest of the graph. Over here at that open circle, well, it's not a part of the graph, so it's kind of like a cutoff right there. Another type of discontinuity that you might run into will be this right here. So this time, you still have your x and y axes just like before. But what will happen is maybe on the left-hand side, you're going to go to some value. And then on the right-hand side, you're also going to go to some value, but a different one. So then you can see that that's what we call a jump, meaning from the left, the limit is not the same as the limit coming from the right. Now for the last one, the one we talked about recently is this right here, where you have an infinity discontinuity. So what that means is graphically, you'll have maybe the left-hand portion go up to maybe like say a vertical asymptote going towards positive infinity. But whereas the right-hand side, you might have something else where coming from the negative infinity, then you have a continuous graph on the right. So in short, that's where you have maybe like say a vertical asymptote. Okay. Now, thinking about limits and how does that apply to all of this, limit coming from the right and limit coming from the left. For removable discontinuity, you can see that the limit as x approaches towards a coming from the left is the same as the limit as x approaches towards a coming from the right-hand side. So you can clearly see that on the map or on the graph that, yeah, coming from the left and coming from the right, the limits are the same and they do exist. But unfortunately, that does not equal to plugging in the value of a into the graph then. So here you can see the limit is maybe equal to some value L. But then L does not equal to f of a because f of a maybe doesn't exist, or maybe it's just somewhere else, or maybe you have like another graph that's up here. So that right there could be f of a. In the case of a jump discontinuity, we have the limit coming from the left-hand side of the function does not equal to, or does not equate to, the limit coming from the right-hand side of the limit. And clearly then, that is not also equal to f of a. So that's going to be the scenario for the jump discontinuity. And finally, for the infinite discontinuity, well, it's basically the same idea. The limit coming from the left is going to be maybe like, say, positive infinity, whereas the limit coming from the right is going to be negative infinity. And again, f of a is going to be undefined at that value. So you can see how, things are starting to tie up now with the whole limit things that we've been doing so far. So let's go ahead and continue on to some of the theorems that you might be seeing then in this section. The first one is called the squeeze theorem. So let me just go ahead and read it first, and afterwards I'll go ahead and give you a picture of what's happening. We're told that if f of x is less than or equal to g of x is less than or equal to h of x, where x is near a, except for possibly at x equals to a, and the limit at x equals to a for the lower function f of x is equal to the limit of x approaches towards a for the upper function is equal to some value L, then the limit at x equals to a as x approaches towards a of g of x is equal to L. So it definitely sounds like it's a handful, a mouthful, but let me just go ahead and draw it so you can see what we're talking about. So here again, you have your axes. So let's say that we have our first graph, which is going to be f of x, and we'll go ahead and draw that in black right here. Now, f of x is supposed to be the lower function, so we're going to go ahead and draw it down to here or over here. Then you have an upper function, which we'll go ahead and call h of x, and we're going to go ahead and denote that in a different color. And let's go ahead and use maybe green this time around because I haven't used it yet. So here is going to be your upper function. Now that is going to be your h of x. And what's going to happen is you're going to have a function in between we'll call g of x in between the two graphs. So let me go ahead and denote that with the final color, which go ahead and use blue in this case. So you can see how g is going to be just somewhere in between. It could be touching them too. It could not be. But basically it's always going to be somewhere in between. Okay. Now, what's going to happen is we're going to focus on a certain value of x where all three of the graphs are going to kind of like, meet together. So we're going to go ahead and call that x is equal to a. And what's given is that the limit as x approaches towards a of f of x for the lower function is going to be the same as the upper function. So that means the limit as x approaches towards a for h of x and f of x are going to be the same thing. So L is located over here. Okay, so now you can kind of see what's actually happening here then. The result is that if g of x is always going to be in between the two graphs h of x and f of x, then the limit at x is equal to a, or as x approaches towards a for g of x, the function in between is also going to go ahead and approaches towards L. So in closing, or in short, it's basically saying that, hey, the function that's in between the two upper and the lower function, if the upper function and the lower function are going to the same y value, then the function in between is also going to have to go to the same y value then. And it's actually pretty important because of this part right here. Sometimes at x equals to a, it's not going to be defined at either function. So that's why I have to say that it is possible that, there could be like a removable discontinuity at that point. Okay. So in some textbook, they call this the sandwich theorem, or in this particular case, we call it the squeeze theorem. So let me go ahead and show you an example as to how this actually work out with an actual problem then. So let me just kind of scroll down over here to this example, right? So here you can see that if you have 2x is less than or equal to some function which we don't know what the equation is, we'll call that g of x, and that's going to be less than or equal to x to the fourth minus x squared plus 2 for all x's that are, I guess real numbers in this case. I want to find out what is the limit at x's approach towards 1. So here's what we'll do then, okay? First, given this inequality, what we can do is we can apply the limit to each part. So limit as x approaches towards 1, because I want to find out the limit at x approaches towards 1 for g of x, of the first function is less than or equal to the limit as x approaches towards 1 for g of x is less than or equal to the limit as x approaches towards 1 for x to the fourth minus x squared plus 2. Note, what I just did was I just basically said, hey, let's look at what happens graphically as x approaches towards 1 for every single one of these functions. Now, the one on the left, that's an easy limit to solve for, because if you remember when we talked about limits, if you're trying to solve for the limit, we always try to plug in the number first just to see if it actually works. And in the case of polynomials, we can always plug it in. So just looking at what we have right here, 2x, we can go ahead and substitute x is equal to 1 with using direct substitution. And that would give me then 1 then. So one would say that the limit as x approaches towards 1 for 2x is equal to 1, which we can replace over here. And for this one right here, on the upper bound, we can find its limit also because it's a polynomial, so we can use direct substitution. So limit as x approaches towards 1 of x to the fourth minus x squared plus 2 is equal to 1 to the fourth minus 1 squared plus 2, which is going to be equal to, looks like it's going to be equal to 2. Okay, so as a result, then that means that the limit of x approaches towards 1 of g of x is going to be somewhere in between 1 and 2 then. So here is our conclusion. So limit as x approaches towards 1 of g of x is going to be somewhere in between the two. Okay. Now, a lot of the problems that you're going to run into, the upper bound is most likely going to be the same as the lower bound. So in that sense, we can actually then apply the squeeze theorem. So for example, what that means is for this problem, if I changed it so that it's not x to the fourth minus x squared plus 2, but rather, let me just go ahead and make a small modification right here. If I change that 2 to a 1 right here, right? And then I would then also change this 2 into a 1. Then what ends up happening is we can now use the squeeze theorem, because the squeeze theorem says that, hey, you know what? If the upper limit is the same as the lower limit, then we can definitely figure out what is the limit in between. So let me just go ahead and change that 2 into a 1. And so now if we have something that's a little bit more concrete, we can then say that, hey, if the limit as x approaches towards 1 of g of x is between 1 and 1, then therefore the limit as x approaches towards 1 of g of x must equal to 1 then. Okay. All right. Let's take a look at another example of the squeeze theorem. So then that way, you can see like more different variations then. So how about this guy over here? The limit as x approaches towards 0 of x squared of sine of 1 over x. Now, this time we don't have an upper bound, we don't have a lower bound, so that could be problematic. If we try to do a direct substitution, just like we've been doing with all the limit problems, we're going to get the following here. We get 0 squared multiplied by the sine of 1 over 0. And that right there is not a finite number, so that actually doesn't work. So the way that we sneak in the squeeze theorem in this case is, let's think about the function sine of 1 over x. Okay. Now, just to make it a little bit easier, I'm going to go ahead and just look at sine of x by itself. I know that sine of x is always between -1 and 1, no matter what you plug in for x. So if that's the case, I want to use that to help me out in this case right here. I can also say that no matter what x is, so long as x is not equal to 0, sine is also going to be in between -1 and 1. Okay, no matter what you give me for x, so long as x is going to be not equal to 0, yeah, the sign of it is always going to oscillate between -1 and 1. Now, taking what we have right there, that is going to allow me to then build into what I want. What I'll do is I'll take this inequality and I'm going to go ahead and multiply everything by x squared. Okay, so the left-hand side, we get -x squared is less than or equal to x squared. Sine of 1 over x is less than or equal to x squared sine of 1 over x. And as soon as I do that, you'll notice that, hey, I'm really trying to set up the squeeze theorem here, where we have an upper function and a lower function. Oh, actually, hold on 1 second. This guy right here is not supposed to be there because we're multiplying by just x squared. Okay, so now we'll go ahead and apply the limit just like we did in the previous problem. Limit as x approaches towards 0 of -x squared is less than or equal to the limit as x approaches towards 0 of x squared times sine of 1 over x, and that's less than the limit as x approaches towards 0 of x squared. Both of these limits on the left and the right we can actually solve for because, again, they are polynomials, so we can use a direct substitution. The left-hand limit, that's going to give us 0, because when we plug in 0, that's what we get, is less than or equal to what we're trying to solve for. So I am going to go ahead and leave the middle part alone because, I don't want to tamper with that. On the right-hand side, limit as x approaches towards 0 of plain old x squared, once again, that's also going to give us 0. So now we can say by the squeeze theorem, okay, the limit as x approaches towards 0 of x squared times sine of 1 over x is equal to 0 because the upper limit and the lower limit are going to be the same thing, and we know that the functions in between will always be bounded by those upper and lower bound. All right, so hopefully that'll give you a better idea about the squeeze theorem. Now let's go ahead and go further into the limit stuff. Some of the problems that you might see that deals with the limit at a single point or at an interval. In order for you to show the function f of x is continuous at a single point x is equal to a, you'll need to show the following. So this is basically kind of like setting you up to be able to do a proof that you might see in your textbook then. So the three things that you have to show will be over here. Number one, limit as x approaches towards a of f of x is equal to some number L. Number two, f of a is equal to L. And finally, number three, that the limit as x approaches towards a of f of x is equal to f of a, because by the transitive property, those two things are supposed to be equal to each other. Okay. Now, to look at it a little bit more further out, I want to say in order to show that the function f of x is continuous on an open interval instead of at a single point from a to b, we're going to have to show that some number c inside that interval from a to b is going to be continuous at that single point. Okay, so this is what I was talking about earlier, how if you want to show that it's continuous in an interval, you don't have to show it for every single number. But what we're going to do is we're going to select an arbitrary variable that's inside the interval, and then we're going to show that the limit exists for that variable. And by showing it for a variable that the limit exists, then that means the entire interval is going to exist then. So we're just trying to show it's going to work for like a general case. So let me show you then how that works then with an actual example. Okay, so let's start first with with the continuity at a single point. The first example would be determined if f is continuous at x equals to a, where f of x is given as that function. And actually, let me go ahead and change that because I think I made a mistake over here. I want to show that, oops, I don't know why that's not working out. I want to write a little bit more, where a is equal to 0. Okay. So in this case, what I want to do is I want to show that this function right here is either continuous or not continuous, okay, at a single point where x is equal to 0. So first off, let's go back to what we're saying over here, right? I need to first show that the limits exist because remember, there are three things I need to show. The limit itself exists at that point, when I plug in, we're going to also get that value of L. And then finally, the two are going to be equal by the transitive property. So let's start first with the easy part. Okay, so let's go ahead and solve for f of 0. Well, f of 0, when I plug in, I'm plugging in not to the first equation, but the second equation, because that's the one that contains 0. F of 0 is equal to 2 to the 0, which is equal to 1. Now, if I find then the limit as x approaches towards 0 of f of x is also equal to 1, then that means that we are going to be good to go. But if it does not equal to 1, then that means that we have a problem then. Okay, so this is what I'm going to need to show, okay, or not need to show, or disprove, basically. So let's go ahead and do that then. Limit as x approaches towards 0 of f of x. In order to find the limit, going back to what we said earlier was, okay, well, we try to plug it in and to see if it actually works. Well, that's only good if it's a continuous function. If this is not a continuous function, and we can show this graphically that it's not a continuous function, we have to do a little bit more digging. So that is to say, the formal way would be to show the limit coming from the left is the same as the limit coming from the right. If you remember from previously, we said that the limit coming from the left of f of x, if that is equal to the limit as x approaches towards the 0 coming from the right of the same function, then therefore the limit is going to exist then. So if these two are equal to each other, then that means that the limit is going to be equal to L. So let's see that then in this case. The limit as x approaches towards 0 from the left-hand side of f of x. So what that means is I need to use the left-hand limit, meaning I need to actually use the first function right there, because x is going to be less than 0 for x that's to the left of 0. So I'm going to go ahead and plug it into x cubed. And when I do so, now we can actually use direct substitution because this is a polynomial. So then we're going to get 0 as our answer. Now we'll do the same thing for limit as x approaches towards 0 from the right-hand side of f of x. But for this time, when I use the right-hand side, I am not using x squared anymore, but instead I am using 2 to the x. And note that when I actually try to plug it in, we're going to get 2 to the 0, which is equal to 1. So unfortunately, because these two are not the same thing, and therefore it's a contradiction. So the limit, this right here, does not exist, what I'm trying to find. So the limit as x approaches towards 0 of f of x is equal to L is going to be does not exist. And that right there is a problem because remember, when I plug in f of 0, that's equal to 1. So therefore, in the very end, this is not continuous at x equals to 0. Okay? All right. Let's now try to do that for the following equation then. Okay? I want to find out determine if f is continuous at x equals 0 for, actually, let's not use f of x is equal to x because that's very plain. Let's go ahead and use absolute value of x. Okay. So here, let's try to apply that same idea. Okay. I am going to need to show the following. Okay. I need to show 3 things. First, I need to show number 1, the limit as x approaches towards 0 of the function is equal to some value L. So let's go ahead and find the limit first. Okay, the limit as x approaches towards 0 of absolute value of x. Now, in order to solve for that, again, we'll use the left-hand limit and the right-hand limit. So what we'll do is we'll solve for each one. The limit as x approaches towards 0 from the left of absolute value of x. Well, our absolute value of x function, we said from a while back that this we can replace with the following. Limit as x approaches towards 0 from the left-hand side is the same thing as negative x because that's what's happening with the absolute value. Okay, here, let me just kind of write that on the side. Remember, f of x is equal to absolute value of x. We can break that into 2 parts. We can say negative x for x that is less than 0, or x for x that is going to be greater than or equal to 0. Okay, so let's see. If I keep going with this, then by direct substitution, the answer is going to be equal to 0. Then, if I'm going to try to find the right-hand limit as x approaches towards 0 from the right-hand side of absolute value of x. Again, we're going to go ahead and change that according to my piecewise function into just plain old x. And when I plug in x is equal to 0 in this case, we're also going to be equal to 0. So therefore, because the left-hand limit is equal to the right-hand limit, okay, so since the limit as x approaches towards 0 from the left is the same as the limit as x approaches towards 0 from the right, then that is going to be equal to the limit as x approaches towards 0 just in general. So that's going to be equal to 0. Okay, so that's going to be my first part. So this one, that's going to be done. The next piece, if you remember, now I need to show that f of a is equal to L. So meaning when I plug it in, it's going to give me the same thing. So if I want to solve for what is f of 0, well, f of 0 by direct substitution into my equation is absolute value of 0, which is equal to 0. So that right there is going to be part 2, which, going by what we needed to show earlier, part 2 was supposed to be that f of 0 is equal to L. So that now works out. So finally, part 3, okay? Since the first answer was equal to 0 and the second answer is equal to 0, then we can finally conclude that limit as x approaches towards 0 of absolute value of x is equal to the limit as x approaches towards 0. Sorry, made a mixed up right here. Limit as x approaches towards 0 of absolute value of x is equal to f, let me just change that one more time, is equal to 0, and then f of 0 is equal to 0, so therefore limit as x approaches towards 0 of absolute value of x is equal to f of 0. Okay, so therefore the function is continuous at x equals to 0. Okay. All right. So that was, probably the more difficult part of what you have to do for this section. So let's now look at the last example over here with the continuity. Okay. This time I want to show that for the function f of x is equal to 1 over x minus 3, I want to show that it's continuous over the interval of from 3 to infinity. So that means that it's continuous, for every single value at every from 3 to infinity. So what we said earlier was, okay, hey, let's go ahead and use an arbitrary value that's in the interval that's given and show that the limit actually exists for that one. Okay, so here's how we're going to start. We're going to go ahead and say let's not use that pen over there. Okay. We're going to go ahead and start by saying let C be a number that's inside the interval from 3 to infinity. Okay, so another way of looking at it is that 3 is less than C is less than infinity. Okay. From what we did before, it's not that much of a difference. So what we'll do is we're going to have to find the following. Okay, I need to first find, let's do the easier one first. What is f of c? Okay, so f of c, according to what we have right there, is just a direct substitution. F of c is equal to 1 over c minus 3. Okay, so that's the first piece. Now, what I want to do is I want to solve for the limit as x approaches towards c of the function f of x and show that it's going to be the same thing. Well, my function is 1 over x minus 3, so that means that this is going to be limit as x approaches towards c of 1 over x minus 3. And since c is a number that's between 3 and infinity, c, I can actually just go ahead and plug in for x then, okay? And I can only do that because c is not equal to 3, okay? So therefore the limit is going to be equal to 1 over c minus 3, okay? And here I'll write a side note also just in case, because c does not equal to 3. Okay. So looking at what we have right there, we're pretty much all set. Okay. We can say that since f of c is equal to the limit as x approaches towards c of f of x, which both are equal to 1 over c minus 3, then the function f of x is continuous at the interval 3 to infinity. Okay. I mean, in ways, showing the function is continuous for an interval is a little bit easier than having to do the limit at a single point. Mainly because there's not a lot of work. So hopefully, you have like a, easier time in this case when you try to do these problems. Okay, so some important notes so that you might want to consider is that the functions are continuous everywhere that we've encountered so far up until this point are polynomials, exponential functions, sine, and cosine. So that is to say that if you ever see these equations, you can just use a direct substitution, and that's actually very key. Anytime you don't have any of these, then you might have to do a little bit more digging. And finally, for this last one right here, this is what's called the intermediate value theorem, or IVT for short. It says that suppose that f is a continuous function on the interval of a to b in a closed interval of a to b. And n is a number, or in a real number, such that n is in between f of a and f of b, where f of a does not equal to f of b. Then there exists a number c in between a and b, such that f of c is going to be equal to n. So IVT is mainly used to show that the existence of a root. So that's where we're going to actually see it. But let me go ahead and draw a picture. So once again, so you can understand what this means visually. Okay. So here is what's happening. So let's say that we have one n, which is going to be at A, and another n, which is going to be at B. And let's say that f of A is going to be somewhere up here. Okay, so f of A is going to be somewhere up here. And then f of B is going to be somewhere down here. Okay, and now it could be the other way around. I don't know. I don't care. All I care is that they're just not equal to each other. Now, the final thing about this is that f is going to be a continuous function in that interval. So what that means is I should be able to draw from one dot to the other without having to lift the pencil. So maybe I can have it go up and then down and then down and then up and so forth, just something squiggly like this. Okay, so it's a continuous function where I don't have to lift up the pen to draw it. So the theorem basically says that, hey, there is going to be a value n in between f of a and f of b. Okay, so there's going to be a value n, and let me just denote that with another color. So let's say that n is going to be somewhere up here. Okay, and the theorem then says that there should exist a number c that f of c is equal to n. And yeah, that's true, because look, somewhere over here, right, if I go across, then there should be a c value where f of c is equal to n. Now, does that mean that that's the only answer? The answer is no, because there could be another one. There could be another one. Then, so what that means is that the theorem states that there is at least one value c that f of c should then be equal to n then. Okay. So for this intermediate value theorem, you're going to see it a lot often, very often on the AP test. So when the time comes, I think we'll go ahead and introduce that a little bit more then. Okay. But for now, that should probably do it. So this is definitely a long video. So thank you for bearing with